Imagine a projectile flying 7 times faster than sound. No smoke, no flash, just pure kinetics. This is not science fiction. It's a railgun. The U.S. was a pioneer in the field, developing a project that seemed to promise revolutionizing warfare, but its funding was cut in 2021. Japan, meanwhile, was just gaining momentum in creating its own railgun, testing it on board its ships. In this video, we'll try to find out whether high-tech weapons in the hands of allies could be the impetus that brings the railgun back onto the Pentagon's agenda, or is the U.S. prepared to watch progress from the sidelines this time? The fleet of the future's not so much about ships as about generating millions of kilowatts of energy. The exchange of missiles has long ceased to be the main headache for the navies of advanced countries. Now their attention's focused on how to quickly detect and intercept enemy ammunition, making a retaliatory strike as precise and painful as possible. To realize such ambitions, powerful power plants and even more powerful weapons are needed. Today, Japan's more than ever at the epicenter of potential threats, from North Korean missiles to China's aggressive policies in the South China Sea, and desperately needs technologically advanced weapons that can intercept targets and launch preemptive strikes. And it looks like the homeland of Sakura has already found it in the form of a railgun. But before we tell you what the Japanese Navy's achieved, let's go back to what caused the American project to be frozen. The railgun itself is interesting because, unlike traditional firearms that use chemical combustion to create force, it uses the principle of magnetism to produce extremely high projectile velocities. This makes the weapon not only futuristic, but also an extremely attractive option, allowing ammunition to be launched over impressive distances with incredible speed and accuracy, while saving American taxpayers huge amounts of money due to the low cost of the projectiles. The first serious research and experiments with railguns in the United States began in 1980 under the direction of the U.S. Army Research Laboratory. The main subjects of interest were plasma dynamics, electromagnetic fields, telemetry, and the transfer of current and heat. But by 1984, they'd shifted to the very specific direction of creating a constellation of satellites to intercept enemy intercontinental ballistic missiles. In the early 1990s, the U.S. Army spent over $150 million on research into electric weapons. The University of Texas at Austin Center for Electromechanics developed military railguns capable of delivering tungsten armor-piercing bullets with a kinetic energy of 9 megajoules, enough to propel a 4.4-pound projectile at 1.9 miles per second. That was enough energy for a long rod of tungsten or another equally dense metal to easily puncture an enemy tank, piercing it right through. By the 2000s, the Navy had taken charge of the railgun's fate, and in 2006, the United States Naval Surface Warfare Center Dahlgren Division demonstrated an 8-megajoule cannon firing 7.1-pound projectiles as a prototype for a future 64-megajoule weapon to be installed on board American warships. A year later, BAE Systems delivered a 32-megajoule prototype to the U.S. Navy. Its blast was nowhere near the force of a nuclear explosion, but comparable to the detonation of 11 pounds of C4. The 2008 to 2010s were no less productive. During this period, the service tested a railgun firing a 10.64 megajoule projectile at 8,270 feet per second, and later followed up with 33 megajoule shots from the same railgun that BAE Systems had previously provided. By 2014, the U.S. Navy finally had ships with the ambition and power capacity to satisfy the railgun's appetite, the Zumwalt class, whose turbo generators could produce up to 78 megawatts. But even they later fell victim to their own futuristic nature and high cost, which is why their numbers were reduced from the original plans for 32 ships to 3 built and 2 currently active vessels. The service didn't plan to stop there, intending to integrate the railgun with a range of more than 100 miles, which was already available at that time, onto ships as early as 2016. Moreover, despite the form factor of this wonder gun, which is quite typical for a ship weapon, its components were largely inherited from the 2006 project tested at Dahlgren. The projectiles here were already more solid, weighing 23 pounds, and flew at a speed of Mach 7. Granted, most destroyers in U.S. service in 2014 could only provide 9 megawatts of additional electrical power, which clearly fell short of the minimum required 25 megawatts to launch 32 megajoule projectiles at a rate of up to 10 rounds per minute. A 32 megajoule railgun shot is equivalent to 23,600,000 foot-pounds, which is comparable to the muzzle energy of about 200,000 22 caliber rounds fired simultaneously. The net power of such a 32 megajoule shot, even fired once every 6 seconds, is about 5.3 megawatts. Now add in the railgun's 20% efficiency in converting electrical energy to kinetic energy, and we realized the ship's electrical supply must indeed provide 25 megawatts as long as the railgun keeps firing. In fact, even if the Navy had retrofitted the Arleigh Burke-class ships at that point with enough electrical power to operate the railgun, the space required to accommodate the additional weapon system would have meant sacrificing existing weapons, so no one was eager to make that concession. What the Navy really wanted most, however, was to add homing capability, something the railgun lacked, to effectively engage distant targets or intercept enemy missiles. As for the price, by the mid-2010s, one such hypervelocity projectile would have cost $25,000, which was still incomparably cheaper than the same Tomahawk missiles, which cost from $1.8 to $4 million. A little later, the idea arose to test the railgun with a pre-installation on a Spearhead-class expeditionary fast transport, but this was soon replaced by ground tests. Overall, the railgun was no wonder of Waffe and the command's understanding, but it was to become an important part of the U.S. Navy's armament, envisaging that future offensive and defensive capabilities would be provided in layers: combat lasers for close-range defense, railguns for mid-range attack and defense, and cruise missiles to provide long-range attack capabilities. Although railguns were also considered as a means of destruction at a distance of up to 100 miles, which would previously required missiles. In the future, the railgun technology was to be expanded to a working range of 230 miles and strikes with an energy of 64 megajoules, which would require super strong gun materials and special capacitors, providing about 6 million amperes of current for one shot. By 2020, the Navy's spending on developing the Wonder Gun over 17 years had exceeded $500 million. And although Congress was not opposed to allocating money for the development of innovative weapons, these funds were clearly not enough for an immediate technological leap. Not to mention that the U.S. military services have focused on developing more practical, but no less destructive hypersonic weapons and combat lasers. The latter have even been successfully tested on board various Navy vessels. In late 2021, it was announced that the U.S. Navy's FY 2022 budget no longer includes any funding for railgun-related research or development. Unfortunately, rapid barrel wear, a lower-than-expected rate of fire, and the enormous amounts of energy required for stable operation put a big pause sign even on such an ambitious weapon. But for how long? The Japanese, meanwhile, decided not to lag behind their allies, having already begun research into railgun-related technologies and basic research into a small caliber railgun with a barrel diameter of 16 millimeters in 2015. However, just 1 year later, it became clear that they would benefit from the experience of their U.S. colleagues, taken as a basis and seasoned with their own technological know-how. So in the same 2016, full-scale development was in full swing. Until 2022, the Land of the Rising Sun was actively conducting research into electromagnetic acceleration systems with the goal of increasing the initial velocity of the projectile while simultaneously improving the strength of the barrel on a single-shot 40mm railgun. And in 2023, the Japanese Acquisition, Technology and Logistics Agency, part of the Japanese Ministry of Defense, announced the successful test launch of its sea-based electromagnetic railgun. The contract, concluded in 2022 by ATLA's Ground Systems Research Center with Japan Steel Works for the research and development of a railgun prototype, was worth $48 million. The result was a muzzle velocity of over 6,560 feet per second for 120 consecutive shots, which fully met the goal set by the Japanese command. Impressively, even after intensive testing, the railgun showed no significant damage to the rail near the projectile's original position, while previous studies have resulted in significant erosion. The test used one 20-foot cargo container as a charger and a 5 megajoule capacitor made up of 3 20-foot cargo containers to fire 2 types of projectiles. Separated projectile, similar to real use with armor-piercing action, and also integrated projectile, simplified in comparison with the previous one to reduce the cost. The steel projectiles themselves weighed about 0.7 pounds. In the future, the Japanese intend to improve the gun for use with a 20 megajoule charge energy. In the spring of 2025, the Japan Self-Defense Forces released an official review of the railgun mounted on the turret of the test ship JS Asuka. The 6,200-ton vessel is a dedicated test bed designed to resemble a real warship and has been used by Japan to develop weapons and other naval systems since it was commissioned in 1995. Unfortunately, there have been no official details yet about the design changes of the railgun presented by ATLA in 2023. Although by external appearances, the characteristics, namely the firing speed of about Mach 6.5 and the use of a charge of 5 megajoules, have been preserved. The Japanese solved the issue of the space occupied by the gun quite practically by securing it to the rear flight deck of the ship, where there was plenty of room to roam. However, integrating a railgun into an operating vessel with a more traditional layout would clearly require some contortions among the components inside the hull. ATLA plans to use the railgun in the future on the upcoming Project 13 DDX destroyers, which will enter service in the 2030s. And in its recent presentations, the agency has repeatedly shown off the Wonder Gun mounted on board a Maya-class destroyer, also known as the 27 DDG class. Last year, ATLA confirmed that it was in talks with the U.S. Navy about using its previous railgun designs, and in 2024 an agreement was signed with the French and German governments to develop railguns. Not to mention that Shigenori Mishima, Vice Commissioner and